Good morning. So, we will continue our discussion on this theorems proved in the thing. We have proved two theorems, Lax-Milgram lemma, basically Stambakia variational inequality, and then we will do a problem, abstract problem in a see for the systems. So, let H V be two Hilbert spaces, and A from H to H, H to R, B from H cross V, keep that in mind. So, looking for a solution in one solution in H and another solution in V for a system. V to R, be two continuous, no ellipticity assumption I am making, continuous bilinear forms. Okay. Let Z equal to, let set of all sigma in H such that B sigma V equal to 0 for all V in V, okay, for all V in V, and this contained in H, okay, it is a subspace. So, we make two assumptions, that we make assumptions. What are the two assumptions I make? The first assumption, one is A is Z elliptic. So, I am not assuming that A is elliptic on H, I am only H elliptic, I am assuming A is Z elliptic, that is A sigma sigma greater than or equal to alpha into sigma, of course this norm is in H square, this happens only for all sigma in Z. This is some kernel, Z is going to be some kernel. Okay, so, that I am assuming in the restricted set. The second assumption is the famous Babuska-Brezzi condition. Babuska-Brezzi condition. This is some sort of a onto-ness condition. We will see that soon. This is supremum of B tau V by norm tau over H. This is over tau in H, okay, and this should be greater than or equal to some beta into norm V, this is for all V in V, okay. So, there exists some beta, there exists beta positive, this is here, there exists alpha positive, that's this is happening. So, these are the two important conditions you have to make these assumptions. Then the conclusion, then for K in H, L in V, there exists a unique pair, okay, sigma u, sigma in H and u in V, such that this bilinear form, such that A sigma tau plus B tau V is equal to K and B sigma V is equal to L, and this happens for all tau V, tau in H and V in V. Okay. So, that is a conclusion. So, this is your conclusion. Let me put conclusions, assumptions, everything separate. Okay. Keep this, there is a so basically what is coming here, analyzing this equation is something of an adjoint, you have to see that. So, looking for this variation is V here, this variation is V here, the variation is tau here. So, it is a solution is here. Okay. V, yeah, so there is one small error, U should be coming here, the solution. Okay. So, this otherwise you see, you do not see the U. Okay. This should be U. Okay. So, the solution is sigma and U. Okay. So, okay. Let me try to prove it slightly because it is a real application of functional, the hard theory of application of the this is a variational form, what is given is a variational form. So, let me give the proof. So, we can make it as an operator. So, you have a bilinear forms produces linear operators, we have already seen. So, you have two bilinear forms, A, B gives operators A from H to H and an operator B from H to B, exactly what we have done for the earlier thing for in the proof of Stambakia, such that okay, A sigma V is equal to A sigma V and B sigma so let me not use for V here because we always keep it there. So, A sigma tau let me write because this is in H and B sigma V is equal to B sigma V. So, you see, keep that A sigma is in H, it works for thing. So, it is for all sigma tau in H and V in for all V in V. So, that is it. So, you have in this operator equation. So, there is a very simple exercise, it is not an exercise, but it is to clear the proof if you have any doubts. So, let me write down the this problem, this is your problem in the variational form. So, let me call it this is to be star. Okay. So, once you have that to be star, so you see the star is can be rewritten as in the abstract form of abstract operator form, rewritten as A sigma plus B star of tau B star of u maybe, yeah, this should be B star. I will tell you where this is work. B star of u equal to k and B sigma is equal to L. So, you have an operator equation. Keep that in mind. Okay. So, where is B star? B star is from V to H is the adjoint. That is B star of V, B star of V will be in H. So, B star of V top so, this is in product in H will be equal to V B of tau. B is a mapping from H to V. So, you have that. So, I call this to be 2. Okay. So, let me call it to be star, because I am calling star for other thing. So, I will call it double star. So, I converted this problem star into a problem double star. Okay. So, let me keep you have more space here, or there was more space here. So, I can do that, or I should have been written here. Okay, fine. So, you have enough space here. So, let me complete and come here. Okay. So, I will go in this direction. Okay. So, B star of E. Now, how is this Babuska-Brezzi condition? So, these are all small exercises which you do. Babuska-Brezzi implies norm of B star of V greater than or equal to beta into norm of beta V, norm of beta into norm of V. This is true for all V in V. This implies immediately, if you are not familiar, check all that, B star is 1 1 and closed range, which are all part of function analysis. Closed range, and again part of functional analysis study, that implies B is onto. So, you see. So, I am starting my proof from here. Okay. Proof. Not from here. Okay. B is onto. So, that implies immediately for L in V, because B is a mapping from H to V, keep that in mind. So, every L in V, there exists, need not be unique now, there exists sigma 1 in H such that B sigma 1 equal to L. Of course, so from here I go here, sigma 1 need not be unique, sigma 1 need not be unique, as we can add any sigma naught belongs to kernel of B. In fact, you have to add. So, you have to readjust your sigma 1 by suitably adding a sigma naught to get a solution of this equation. So, you got one solution to this one, and that solution immediately will not satisfy the first equation in star. So, you have to, so what do you do is that look for sigma naught in V, sigma naught in B, which is of course is a subset of H, keep that in mind, sigma naught in V and U in V such that sigma is of the form sigma naught plus sigma 1 and A sigma plus B star of U equal to K. So, that we have reduced this problem to this form, that is what you do it. So, here is another simple trick, we are going to use this one. Now, consider this is slightly a complicated proof, but so consider A sigma plus a consider this equation A sigma naught equal to without your B star. So, I consider A sigma naught plus sigma 1 this equation. is equal to k, k is given to you, I just remove B star. In other words, you consider A sigma naught plus A sigma naught equal to k minus A sigma 1. Okay. Now, I consider this equation not on whole H, I consider this equation on Z. What is the reason there? I do not have the ellipticity of A in H, but I have an ellipticity of A in Z. That is what is given. Yeah, that point maybe I have to say that. So, the ellipticity of thing, so let me write down. Okay. So, let me write this, continue from here. So, you have this problem, this what you want to do, that one, this is equivalent to, the last one is equivalent to A sigma naught tau equal to k tau minus A sigma 1 tau for all tau in Z. This is contained in H, that is what you are going to do it, and A is Z elliptic, which is given to you. This is the assumption 2, Z elliptic, that implies there exists a unique sigma naught in Z. That is what exactly you want it, but the problem is A sigma naught is in Y. So, this equation what you have seen here is in Z, okay. So, what about this now, the thing, so you define sigma is equal to sigma naught plus sigma 1. What about this one? What is given is that this is an element in H, okay. So, A sigma plus A sigma equal to k, okay. So, I want to look for this equation now, I want to consider, we need existence of u, so that this is equal to k. This is what we want to prove it, but what you have done is that A sigma equal to k in Z, and Z, if you observe, this is nothing but the kernel of P. So, that implies your A sigma minus k is in kernel of Z perp, that means kernel of B perp. Okay. You can conclude that only, you cannot conclude A sigma minus k is equal to 0, and that is not what we want it. So, the kernel of B perp, and again you recall the results from here, this is nothing but range of B star. So, this implies there exists an element u, of course uniqueness is guaranteed right now. So, we are only proving the existence, there exists u in B star such that A sigma minus k is in equal to minus B star of u, you can write because of the linearity. So, minus B star of u, or you can write A sigma plus B star of u is equal to k. Indeed, A B sigma is equal to L, because B sigma naught is equal to 0. Okay. So, that is the point. So, this does not prove immediately uniqueness, but I will leave it the uniqueness part to you to prove it, you prove directly uniqueness. Suppose there exists sigma 1 sigma 2 and u1 u2, define the standard way of proving uniqueness, define sigma tilde is equal to sigma 1 minus sigma 2 and u tilde is equal to u1 minus u2. Okay. So, there is some work involved, but I want you to leave it as an exercise. It is a bit you have to prove that one. Exercise, prove sigma tilde equal to 0, u tilde equal to 0. Okay. So, that is a Babuska-Brezzi theorem. So, go through the proof, understand. If you are not familiar with and this whatever is there, that so it is not completely new to you. In an infinite dimensional setup these things may be new, but in finite dimensional setup this is not completely new, because suppose you want to solve it Ax equal to b, you see for a matrix A, it is a matrix A. Then if A is invertible, I think I made this remark already, but I am again once more making, if A is invertible then there exists a unique solution, but if A is not invertible, A is not invertible, then this has a solution. If as a solution, of course if you have to have your B has to be in the range of A, of course that is a thing, but from here you can see that that is equivalent to P is kernel of a transpose, right. So, you have to look at the solutions of a transpose of x equal to 0, and it should be orthogonal to the solutions of these homogeneous equations. Okay. So, that is what we are looking at it. So, these are all results that kernel B per piece range of A B star are all coming from there. So, we will be applying this theorem at some point of time, and now we want to apply this result for the weak formulation, weak solutions. So, you have to how to apply that. So, I will prove it for some boundary conditions. You should also work with other solutions. Recall L naught of u in second order linear elliptic operator in divergence form as d by dxi of Aj of x du by dxj equal to f in omega and u equal to 0 on d omega, and this is the equation you want to study. So, what are the assumption? Aj is symmetric. Symmetry you do not need to assume. Aj is elliptic, that is the important thing, elliptic, continuous. You are assumed and you are given the definitions of that. So, you start with so what is the space you are looking for? So, you are looking for the space from the motivations from the previous course as well as from this course. Now, you are looking for a solution in this Sobolev space, because to take the boundary condition. So, you are looking for plenty of motivations are given u in H1 naught space. So, that is your Hilbert space. So, you look for solutions there. So, how do you get a weak formulation? Choose and you assume f is in L2 of omega. Actually can assume f is in H1 naught dual, that is also possible, okay, and that is dual, and that is nothing but your H minus 1. So, whatever analysis I am doing here, it also works for H minus 1 of omega. The only thing is that instead of an integral or an inner product in L2, you have to work with the duality bracket between H1 naught and H minus 1. That is all you have to do it. So, how do you get the weak formulation? We have done already, but now it is a more we are actually going to prove the existence by applying the Lax-Milgram lemma. So, multiply this equation star by V. You can do it V in first you start with V in smooth, and then you can see that by density thing. So, and you apply V from H1 of omega, integrate by parts to get the weak formulation, integral of Aj of Ux du by dxj dv by dxi equal to Fv, integral of Fv. No boundary terms. This is your Fv. Fv is in an L2. You can take L2 actually. Okay. And this is your AUV. So, your problem is, so that implies you look for U in H1 naught of omega such that AUV is equal to Fv for all V in H1 naught of omega. You see. So, you have to prove the existence. So, to prove the existence you need continuity and boundedness, right. To prove existence only two conditions. To prove existence uniqueness, how do you do that? You have to prove the continuity of AUV is equal to modulus of Aij du by dxj dv by dxi. Now, apply boundedness of Aij. This is less than or equal to m into norm of grade u, sum it everything, L2 into norm of grade V at L2, and that is less than or equal to m into norm of u at H1 naught into norm of V at H1 naught. V at H1 naught of omega, and that is continuity. What about ellipticity? Continuity. So, you have to prove H1 naught ellipticity. Okay, so we need to prove H1 naught ellipticity. How do you prove that one? So, you have to compute AUU. This is equal to integral of Aij of x du by dxj. I am again repeatedly writing. First time du by dxj I, and this of course you know that by ellipticity this is alpha into norm of grade u square. You see. So, you have that, but what we need is this one. This is the question. This has to be replaced by some constant alpha prime into this is L2. Okay. So, norm of u in H1 naught of omega square, and this follows by Poincare inequality, where Poincare inequality. If you are not convinced and if you are studying first time, Poincare inequality norm u at L2 is less than or equal to norm grade u at L2. So, you can estimate some grade u but you can put it no mu. So, this can be proved. If not, do it as an exercise. If you are learning for the first time, you have to do it that way. So, you have a thing that implies there exists unique u. This is by Lax-Milgram. There exists unique u in H1 naught of omega such that AUV is equal to FV for all V in H1 naught. Okay. So, there is a continuity estimate, maybe we will do it later for the when I assume even the non-homogeneous case situation. You can actually prove, we will do this later, actually you can actually prove that norm of u in H1 naught norm can be estimated as constant in u. It is almost there, but you can actually get immediately also. You can have, this is your continuity estimate for the well posedness. Hence, this problem is actually well posed. Okay. Should I do something more? Yes, one more, a couple of remarks, then I will stop. If A is elliptic, no, if A is symmetric as well, if A is symmetric as well, then U can be characterized by, U in H1 naught of omega, and then Ju is equal to minimum of Jv, where the minimum is taken over H1 naught or only when it in the symmetric case. And what is your Jv? Your Jv is equal to half of integral of Aij of x dv by dxj and dv by dxi minus integral over fv. So, you see, you get the minimization problem in the case of symmetric case. And yeah, so as I said, you can actually get, this case you can prove it. So, maybe I will before coming to the next class, you try to get this estimate as an exercise. We will show you when it is studied full non thing, when we study L naught of u equal to f in omega and u equal to g on, I will make remarks on d omega. I will also make something, when you get a strong form, you get a weak form, and it is also important to show that if the solution is smooth, you should be able to get back your strong form. Then you will basically say that your weak form is a genuine weak form of your strong form. So, you should be able to go back, every strong form will give you the weak form under suitable multiplication or whatever be the definition, but when the solution is smooth, you should be able to go back to get your strong form. Okay. So, I will stop here and then we will continue these things with the different boundary conditions and for some other systems, etc. Thank you very much.